So good afternoon, everyone. Today, the Atom Seminar has the great pleasure to welcome Professor Peter Cummings. He graduated in mathematics from the University of Newcastle and obtained his PhD also in mathematics from the University of Melbourne. I'm sorry. He holds the position of principal scientist in the Center for Nanophase Material Sciences at the Oak Ridge National Laboratory, as well as the position of founding director of the Nanomaterials Theory Institute, the CNMS Theory Program. Professor Cummings currently works as a professor of chemical engineering and associate dean for research for the School of Engineering at Vanderbilt University. His research interests include statistical mechanics, computational material engineering, and theoretical nanoscience using molecular modeling techniques such as molecular dynamics and Monte Carlo simulations. He is the author of over 320 journal publications that have been cited almost 80,000 times since 2016. He has received many awards and has been elected fellow of the American Physical Society of the American Association for Advancement of Science and the American Institute of Chemical Engineers. So once again, welcome Professor Cummings. Thanks so much for being here, and please feel free to share your screen and start your presentation.
Thank you very much. And I'll just start sharing my screen. I'm sharing my screen, I hope.
Yeah.
Is that showing? Let me just restart the screen sharing because it's not looking the way well, hang on just a second. Okay, are we all set then? You can see my screen. Okay. Well, I want to thank the organizers for giving me the opportunity to talk to you today about the molecular simulation design framework. I am the PI on this project, but there are many people involved, and hopefully I'll get the chance, and some of whom are on this seminar today, and hopefully I'll get the chance to acknowledge them as we go along. This molecular simulation design framework is something that originated with our desire to be able to do computational materials discovery. Within the United States, there's this initiative called the Materials Genome Initiative, which is now 1 decade old. The goal of the Materials Genome Initiative, or the MGI, is to bring new materials to the market twice as fast and at half the cost, and to use computational methods to do this. And I have listed here a couple of examples of these kinds of MGI projects. The most famous one is the Materials Project. And these are typically you have computational screening of large numbers of systems. In most cases, these are hard materials or single molecules. So the first two here, the Materials Project and the MoSDeF screening, these are hard materials that are being screened. In the first case, using low-level electronic structure methods with the goal of identifying materials that are useful as electrodes in batteries. In the case of MoSDeF, it involved doing Monte Carlo simulations on many hypothetical MoSDeF structures, but the structures themselves, the ones that are essentially being screened, are hard materials. And this is looking at methane storage. And then the last one is looking at single molecules, looking at candidate compounds for organic photovoltaics. In all of these cases, what's being connected is you need a connection between the chemistry of the system and the conditions and the properties that you want to screen over. If you think about this, trying to do this now for soft matter, things that are deformable. So we're talking about biomolecules, liquids, polymers, etc. Part of the problem is that for soft matter, the predominant physical behaviors occur at energy scales comparable with KT. Unlike hard materials where the things that bind them together are many KT, and so they're typically going to be in a crystalline state. The weak dispersion forces frequently dominate, and this is part of the reason why they're comparable with KT. So it can be difficult to predict structures simply from atomic and molecular constituents. And so this connection between chemistry and conditions and the properties of a soft matter system is a non-trivial connection. It's not a straightforward thing to do. And I have just there we go. Sorry, I just it froze for a second on me. So we've been developing this MoSDeF, the molecular simulation design framework, for almost a decade now, where the idea is to develop a platform to perform MGI type screening on soft matter systems. And typically in the past, this connection in a soft matter system between the chemistry and the state conditions and the properties has often been done as a kind of cottage industry. With a graduate student will be given a system and asked to develop a molecular simulation of that system and calculate the properties. We, in order to do MGI style screening, need to automate a lot of these steps and do them in a way that's completely transparent and available for other people to adopt and use. And so what we've been doing is, there we go. The thing with soft materials is that the connection between the chemistry of the system and the properties usually takes quite a number of steps. First, you have to figure out what the force fields are, and that's either gathering force field information from the literature or deriving it from ab initio calculations or experimental data. Then setting up the simulation, initializing it, equilibrating it, performing production runs, and then doing statistical averaging in order to calculate the properties of interest. And so this is a complicated set of steps that has to be done in order to connect the chemistry to the properties. So to develop this platform for doing MGI type screening, as I said, we need to be able to automate these steps and combine them together. And we were inspired by the software engineering field of model integrated computing. This is a technique of software engineering that was developed by researchers here at Vanderbilt in the Institute for Software Integrated Systems. And it's used in a wide variety of applications. I've given some of them here: assembly line automation, health records management, and so on. And the thing about model integrated computing is it involves meta language abstraction, where you abstract the whatever the application is to a higher level. You use domain-specific markup languages and things like this, and then you're able to chain these things together as you need to do in the case of the molecular simulation. And this is being funded by three, and it's the work that we're doing is the outgrowth of 3 NSF grants, each of which was joint with ISIS, the Institute for Software Integrated Systems, not the terrorist group in the Middle East. And the other thing that MoSDeF also seeks to address is the reproducibility of simulations. And so the question is, how does it do it, and why is it important? Well, as you probably know, there's been a lot of discussion in recent years about the reproducibility crisis in scientific research, that a lot of the work that's reported in scientific journals can't be reproduced. This is particularly the case in experimental research, but it's also something that's a problem in computational research. And so reproducibility in computational science is becoming a forefront issue. Amongst the, if you look at this literature, amongst the things that people say is that automation is a key device for reproducibility. Automate as many steps as possible. That way other people can repeat them easily. All the details of the computation must be made conveniently available to others. And then Lorena Barber, who's one of the most vocal people in this area from George Washington University, she has a blog about this. And what she once made the statement, I saw her give a talk in which she said, GUIs, graphical user interfaces, are the enemy of reproducibility. And I can expand on that in question time if somebody's interested in this. But MoSDeF is characterized by everything being scriptable, everything open source, complete data dissemination, so that people can reproduce the simulations. These are all things that we are inherent to MoSDeF. So originally our motivation was to be able to study interfacial systems. This was in order, we'll see later on the application. And so this is what started us on this path, is that the existing tools for setting up simulations didn't have the kind of functionality that we needed to be able to do our sorts of simulations. So we need to be able to do surface functionalization. We wanted a lot of the systems that we were doing, we had to do some force field development on because they didn't exist for the systems that we wanted to model. And so that got us interested in disseminating force fields. We want to use different simulation engines. I think everybody who does molecular simulation swaps around between using code like LAMMPS or UMD or GROMACS, and depending on the property being calculated and so on. So we want the system, MoSDeF, to be simulation engine agnostic. In other words, it can be used with a wide variety of simulation engines. It's open source itself, and it's built on open source components, so everything is available online. And I'll just make one brief statement about force fields. I mean, which anybody who does molecular simulation knows this, but you know, the force field, which is a description of the potential energy of the system, has lots of components in it. It has bond stretching, bond bending, torsional potentials, improper potentials, which prevent molecules, certain configurations of the molecules that and then you have the van der Waals forces and Coulombic interactions between atoms in the system. So there's a large, the thing is, if you're looking at any kind of complicated system, any kind of complicated molecule, an ionic liquid is a good example, you may be talking about hundreds of these parameters that need to be specified in order to accurately model that system. And that's something that where mistakes are continually made in the literature when people perform simulations. And so one of the things that we've been trying to do with MoSDeF is to eliminate the errors that come about through trivial mistakes in force field application. So the three tools that we've been developing under the MoSDeF suite, MBuild, a hierarchical system for constructing complex molecular systems, FOIA, which is a general code for applying a force field with the proper force field parameters and disseminating them. We built something called Meta MDS, but we've subsequently dumped that actually in favor of SINIAC and SINIAC Flow as a workflow management system that was developed by the Blotzer group at Michigan. And this is a system which enables you to run multiple simulations simultaneously and manages the execution and the data of those systems. We use a whole lot of other open source software, many of which you have probably seen yourself. and we use the Python scientific stack, and so on. So we use a lot of existing open source tools. We've also been involved with modifying these open source tools so that they're more flexible and able to be used more effectively by us in MoSDeF. So if we look at this series of steps that's needed to perform a molecular simulation, whether it's molecular dynamics or Monte Carlo, the first thing we have to do is relate the chemistry of the system and take the chemistry of the system and initialize the system. And to do this, you need to build a system, and that's what we call mBuild. That's what the role of mBuild is. Foyer is the application of the force fields, and then to do the putting all these things together in order to execute the simulations is the role now of, was the role of Meta MDS for us, but now it's SUNYAC and SUNYAC Flow. So let's talk briefly about mBuild, and I am going to be very brief about this. I have way more information than I can possibly go through. I'm glad that this is being recorded so people can go back and take a look at these slides later. But I want to try and give you at least a flavor of each of these components. mBuild is a hierarchical molecule builder. You can build up complex systems like this one shown here of a brush system on a, in this case, a beta cristabolite silica surface. It's built around things being built up from smaller components. You can combine things into much more complicated structures. The important thing is that everything is done with scripts. And so this just gives an example of the kind of thing that people, this is a polymerization script that's been developed over the years within the MoSDeF community. And I really don't have time to go into the details of this, but you can find information at the mBuild part of mosdef.org. But what this enables you to do is build up a complex polymer molecule from its components, from the monomers and the N groups. We particularly are interested in things like interfacial systems where you have a solid surface to which we have attached things like alkyl-silane monolayers. And the idea is that because this mBuild is hierarchical, you can keep adding levels of complexity that each one of those levels of complexity can be abstracted at the next level up. And so you can, if you look at these two systems down here, these alkyl-silane monolayers attached to a silica surface. To build these two different surfaces here, you can, it only takes 3 lines of code in mBuild because it's relying on the fact that we have built up these components and all of these things are available within MoSDeF. You can build up these fairly complicated systems with relatively small numbers of lines of code. And the thing is that once this code is done and available and in MoSDeF, someone else who wants to come along and do a simulation of these systems can build exactly the same system that you built because they can use the tools that are in MoSDeF. So this is important that these recipes are easily shared and reproduced. This is another example. This is from work of Claire McCabe, for example, where here she's building, two bilayers. So it's a bilayer and another bilayer. Each bilayer has, in this case, ceramide molecules that are part of what happens in the self-assembly of skin. This complicated system here can be built in just 18 lines because, again, of all you're abstracting up from things that have been done before, and so this hierarchical hierarchical property of mBuild is extremely important. And again, it makes it reproducible. Foia, which is our atom typer, it's a general purpose atom typer. And what we want to be able to do is apply force fields and apply them in such a way that they are applied with all the right parameters. As I said, the number of parameters that exist in a force field for a complicated molecular system can be of order of 100 or more. And so getting all those parameters right is a big problem in a lot of molecular simulations, particularly for people who are just starting out in the field. There's also the problem that there are typos in the literature. And so what we need is a way to store these force fields and make them available to other people, and make sure that what we're doing is using the correct parameters, not the ones that may be published in one particular paper. In a lot of, we have, working with the computer scientists in ISIS, we modified the way in which we created the way in which FOIA works based on something called overrides, and I'll say something about that in just a moment. But to show you just a very simple example of applying how easy it is to apply a force field in MoSDeF, this is here. All you're doing is loading the structure of methane. Sorry, let me go back. Structure of methane. You're specifying that you're going to use the OPLS all atom force field, and then you apply the OPLS force field to that ethane molecule, and now you have ethane with the force field applied, and so you can save it to any format that's supported by PARMED, and so you can save it to a topology file and a GROMACS file. And so it's very easy to apply force fields within MoSDeF, even to very complicated systems. This is obviously a very simple system. So what we did is we expanded the OpenMM XML, which is an existing infrastructure. And what we did is we added smarts as the method for describing the topology and chemistry of the system. And so this is just a snippet from the OPLS force field, for example. And this is the smarts definition that tells you what we're looking at here, what molecule we're looking at. I don't have time to go into this in a lot of detail, but this particular OPLS, you know that for a carbon, there are literally hundreds of different carbons in OPLS, depending on where they exist in the molecule and so on. This is the toluene CH3 one, and its name is OPLS 148, and it overrides OPLS 149 and OPLS 135. And there's a DOI embedded in the XML that tells you the source of the publication for the force field parameters. You can see the parameters down the bottom here. And then we actually have included in FOIA, if you atom type a system, you can then run a code that will then tell you, will accumulate for you a BibTeX file, which contains all of the articles which define the parameters that are used in the force field that you're using. So it's very convenient from a publication point of view. And what happens is that in FOIA, basically, it looks at each atom in the system. It develops something called a whitelist, which is all the things that could be, and then a blacklist, which is all the things that can't be because of overrides, and then it compares those two, and you're left with one possible thing that it can be, and that gives you the parameters for that particular atom. So there's a lot of information on how to develop these FOIA compatible force field files. There's tutorials and so on. it's also a great way of disseminating force fields. Like we've developed force fields over the years in our group, and we can disseminate them through FOIA. It means that when somebody else pulls them out of FOIA, they're going to get exactly the parameters that we defined. And we also have the capability of giving the force field a DOI, so that in a publication we can refer to that force field, and then it will then take you to that force field data in FOIA, so that you can use that force field and know that you're using exactly the same force field as was published in the paper that first presented that force field. So this is, we do a lot of work in, I do a lot of work in supercapacitors. Claire McCabe does a lot of work with coarse grain models for skin lipids. And so these are ways in which we can disseminate those force fields. So more recently, one of the things that we've been developing as part of MoSDeF is something called the General Molecular Stimulation Object, GMSO. We have in the past relied a lot on PARMED, but PARMED has a lot of limitations. In particular, it only allows 12-6 Leonard-Jones for non-bonded interactions between atoms in a system. So that's not useful if you want to use exponential 6, for example. So GMSO addresses these limitations. You can.
Hey, good. How are you?
Oh, Heath, how are you? You can define functional forms using symbolic mathematics, and if a simulation engine supports it, it can be done with it can be written to from GMSO, and GMSO is GMSO is under active development at the moment, and we're working with these simulation codes. WMD Blue, GoMC, GROMACS, Standard and LAMPS, to create writers from GMSO to those different simulation codes. And so you can learn more about that at gmso.mosdef.org. And we're also working closely with the Open Force Field group to extend, to find a way in which FOIA and the Open Force Field group can work together to define these more sophisticated force fields. And the last thing is meta-MDS and SINIAC flow. The old meta-MDS is no longer being used, so I'm going to just jump through this. But I mean, the idea of meta-MDS, this is what it looked like, is that if you wanted to do a simulation of a system with for different chain lengths, and using the OPLS all-atom force field, you could do that with this kind of code, with a very short amount of code, and running it on, in this case, a local server. So the idea was that this is would enable you to do computational screening. But as I said, we decided that SINIAC, the code that's developed in the Glotzer group, was much more powerful and worked on much bigger machines, and so we switched over to there, and it's the same concept. It's just a lot more sophisticated, and in particular, it's sophisticated in its data management tools. So if we put all this together, we can do all these things. We can build a system, save it with FOIA, do things like energy minimization, equilibration, etc. And this is what we do with our tribology simulations, and this is what the output looks like at an intermediate point with SINIAC. We have got MoSDeF and SINIAC on all sorts of environments, so that people can make use of them in NERSC, the National Energy Research Supercomputing Center, the Oak Ridge Leadership Class Facility, and so on. So these tools that, I mean, they are, you can install them yourself, or you can use installations that have been put in those environments. So we've been trying to build a community for MoSDeF for some time. It began with a hackathon in 2017 with representatives from 11 research groups and ExxonMobil. We developed a sort of wish list of things we wanted to do with MoSDeF. We wanted to support more force fields. We wanted to have workflows for all sorts of applications and specific properties, such as coarse graining and so on. We wanted to add more simulation codes beyond LAMMPS, GROMACS, and UMD Blue, which is what we were using in our own research group. So we got an NSF grant to support this next round of development of MoSDeF. It involves University of Michigan, Notre Dame, Wayne State, Minnesota, Boise State, Delaware, and Houston. And you can see the various contributions there. And one of the things you note there is several Monte Carlo codes, the Cassandra code from Ed McGinn's group, the GPU optimized Monte Carlo code from Jeff Potoff's group, CP2K, the Car Parallelo 2K code, of which Siepman is one of the developers. Ilya Siepman is one of the developers, and I see that you had both Ed McGinn and Ilya Siepman speaking in your seminar series, and so the idea is that this group, because they have a lot of different capabilities and a lot of different research interests, are all working towards expanding MoSDeF and enabling reproducible science using the MoSDeF tools. And so here is the big picture of MoSDeF. You build a system, apply the force field, use Gmsl to edit and save your parameterized system, and then these are the simulation engines that we are currently supporting. So I want to now talk very briefly about a couple of applications. One is nanotribology. This is relevant in the lubrication of nanoscale devices when you have two surfaces moving with respect to each other at distances of the order of nanometers. How do you lubricate those kinds of systems? Traditional lubricants aren't going to work because you know, an alkane, for example, will solidify when between two surfaces that are of the order of 1 or 2 nanometers apart. So one of the things that, one of the ways in which people have looked at lubricating these is with monolayers. You know, like alkane thiol monolayers on a surface, alkysilane monolayers on silica. Putting these things between two surfaces can reduce friction by half the friction or less compared to that of bare silica. This is the coefficient of friction. There's issues about how durable are these coatings, but what we're going to firstly be concerned about finding surfaces, finding functionalizations which will give low coefficients of friction. So we want to do MGI style screening of monolayer lubricants using the MoSDeF toolkit. And so the way in which we're doing this is we're doing molecular dynamic simulations where we have two amorphous silica surfaces to which we functionize alkylsilane molecules, and then we undergo shearing and we calculate the friction forces from the simulation. And we do this at constant applied normal load. Now, from these simulations, what we find is that the friction force versus the normal force follows a straight line like this. And the thing about this is that the slope of this, well, the intersection of this line with zero normal force is what's known as the adhesive force. And then the slope of the line is the coefficient of friction. And so we can extract the coefficient of friction and the adhesive force from several simulations done at different normal forces. And this equation here is Amonton's law of friction. So we analyze our simulations according to this equation here. And there's been some work in the literature already experimentally. One of the things that's been observed is higher frictional forces in hydroxyl terminated monolayers, which is attributed to hydrogen bonding across the monolayer interface. Phenyl terminal groups can improve durability, but really from an experimental point of view, very few chemistries have been studied in the context of lubrication. So what we did is we looked at alkyl-silane tethers, and we looked at these different functional groups as the N group, as the terminal group. So there's 16 different groups here. And we also looked at varying the length of the tether, varying the length of these alkyl-silanes, and looked at the tribological properties. So if you want to think of this as a simple representation is we have these silica surfaces here, amorphous silica surfaces, to which we have tethered these molecules with these different terminal groups. And the gross results from those simulations are summarized here. A coefficient of friction as a function here of chain length. It goes down. As the chain length is increased, and in fact, experimentally, the systems that are studied experimentally are all around 17 or 18 carbons in length. So these gross results here, which summarize all of the simulations, suggest that the longer chain lengths are going to give the lowest coefficient of friction. For the adhesion force, it's largely independent of chain length. And then the orientational ordering increases as the chain length increases, the orientational ordering within the monolayer. So if we have a look at the effective terminal groups, this is looking at the coefficient of friction and the adhesion force sorted from lowest to highest. Okay, and then you might ask, what's the trend here? What's going on? Well, one of the things that hydrogen bonding groups, they're all at the top end of the adhesion force. And the adhesion force, I think you can sort of I think of it as a thermodynamic property, whereas obviously the coefficient of friction is a transport property. And so hydrogen bonding is not a predictor of the coefficient of friction, for example, as you can see from here. How about polarity? Again, all the highest adhesion forces are polar molecules, but the polar molecules are all over the map, so to speak, in terms of the coefficient of friction. So simple explanations don't work here, at least in terms of the transport properties. We can look at aromatic groups, no big pattern there, and so on. So what we did is we increased the sampling by also considering two monolayer systems in which the functionalization was different on either side, okay, as shown in this cartoon here. So that adds 100 different interface pairs. And remember, we're doing these simulations at 3 different normal pressures, and doing replicates, I think, of the order of 3 to 5 replicates per simulation. So we're doing a lot of simulation. It turns out something around 800 or so simulations are being performed to obtain this data. So to try and understand what's going on, we use structure property relations. We use the RD kit, open source RD kit. We assign molecular descriptors to each terminal group that are based on things such as shape and charge distribution. And so some of these are illustrated here. And from that, then we can use a machine learning algorithm, something called the random forest technique, And using random forest, we are developing predictive models for the coefficient of friction and the adhesion forces. And what happens with the adhesion, with the coefficient of friction, is the thing that turns out to have the biggest impact on the coefficient of friction is something called HK alpha mean, and that relates to the hybridization of the N group. So things with SP hybridization have lower coefficient of friction than things with SP2 hybridization, which have lower coefficient of friction than things which have SP3 hybridization. And you can think of SP as being linear molecules, SP2 as being planar molecules, and SP3 as being three-dimensional molecules. I often use the term pencils, paddles, and bobbleheads to describe this, and that's usually to the horror of my graduate students. But once you see that, then you understand what's going on. If you look at if I go back to, if I can go back, I don't seem to be able to go back very well. You would see that the thing with the lowest coefficient of friction is the cyano group, which is simply like a pencil. And so, and I think it comes down to the fact that this is a transport property. And so really what's becoming the most important thing is the repulsive forces and the shape of the repulsive forces between the molecules. And this has been published in JCTC just last year, was primarily the thesis work of Andrew Summers. And also in the adhesion force, we find that it's dominated by TPSA min, which is a charge distribution, and hydrogen bonds. These are the two major things. And as I said, this makes sense. I mean, when the molecules are facing each other, if you've got hydrogen bonding going across between the molecules or polar forces between the molecules, that's giving you a higher adhesion force. And so, but that we already saw that to some extent in the raw data. What we didn't see in the raw data was the way in which shape was playing a major role in determining the coefficient of friction. So we found that really great, that we learned something that we could understand in the end from a chemical point of view. We've been looking at other aspects, different tether chemistry, looking at monolayers, which are mixtures, asymmetric functionalization, as a result of which we've done using the MoSDeF tools and the SIGNAC, we've performed about 120,000 total simulations, which are just about finished being analyzed, and we're ready to, we have a paper just about to be submitted, putting together a really much broader model, machine learning based model for the relationship between chemistry and transport and adhesion force properties of these systems. I'd like to just very quickly say something about diffusivity of solvated ion liquids. That's also been done with MoSDeF doing screening. This is part of our work in the Fluid Interface Reaction Structure and Transport Center, where we study supercapacitors. Supercapacitors store energy like capacitors, but they're supercapacitors because the electrodes are highly porous, nanoporous, and so they can store, and the ions are stored in the electrical double layers within those nanoporous electrodes. They have a high power density because the charging and discharging of these can happen extremely rapidly, but typically lower energy density than batteries. And so what we're trying to do is improve the energy density whilst not losing the power density. And ionic one of the electrolytes that are being used in modern supercapacitors is ionic liquids. because they have high electrochemical stability. They're stable up to about 4 volts, but they can have slow transport properties. And so one of the strategies that people use when it comes to ionic liquids is as electrolytes is instead of using neat ionic liquids, as shown here, we look at these in organic solvents, because that, and you can see just from this simple simulation here of a neat ionic liquid on the left-hand side and the same one dissolved in an organic solvent, you can obviously see that the ions move much more rapidly within the solvent. And so the first study we did on this back in 2016 was we looked at 4 different organic solvents, you can see here. And we looked at one particular ionic liquid. And we used a technique called quasi-elastic neutron scattering, QENS. And we measured the diffusivity of the positive ion, the BMEM ion. And we found in the QENS that it was correlated with the dipole moment of the solvent. We were able to kind of motivate that from the point of view of a higher dipole moment of the solvent, the better dielectric screening there is of the ion-ion interaction, and therefore there would be less ion-ion pairing in higher dipole moment systems. Obviously, also the cation diffusivity decreases as its concentration increases. I mean, this is dilute ionic liquid through to concentrated and then to pure ionic liquid. The diffusivity is changing, you can see here, by 1 or 2 orders of magnitude. So we decided to look at a much larger chemical space. So we looked at, instead of just 4 solvents, we just decided to do this computationally. We looked at 22 solvents instead of 4 compositions. We looked at 18 compositions, which meant we had 396 unique systems. We used MoSDeF and SINIAC, these are just some details of the simulations. This work was primarily done by Matt Thompson, who's now graduated and is in the Open Force Field Consortium. And so this shows ion diffusivity as a function of ionic liquid composition for all of these different solvents. All of these results will come to the same point at mass fraction 1, because that means you're at the pure ionic liquid. But you can see that just as we saw in the earlier study, diffusivity is varying by as much as a couple of order of magnitude as you go from dilute solution to neat ionic liquid. We then looked at how this ion diffusivity compares with solvent polarity for this large data set now. And you can see that there's basically no correlation. Every one of these points corresponds to an ionic liquid given by the color, and then concentrations going, 18 concentrations going from dilute to concentrated ionic liquid. So these are the dilute systems up here, and at the bottom is the pure ionic liquid. But you can see that there's no pattern there with solvent polarity. On the other hand, if you plot versus solvent diffusivity, you can see that there is a clear trend here that the ion diffusivity is increasing with the solvent diffusivity. And you can motivate that because this means that the ion diffusivity is inversely proportional to the solvent viscosity because of the relationship between diffusivity and viscosity of the solvent. And this is something that you would expect based on Stokes-Einstein, at least in the dilute regime, these points here. But in fact, this correlation is taking place over all concentration regimes. If you look at now conductivity as a function of ionic composition, we see this effect that we saw before, namely that at high concentration or near neat ionic liquid, the conductivity is low because the viscosity is high, the diffusivity is low. At the other end, it's low because the number of charge carriers is low. The sweet spot is somewhere in the middle where you have a large number of charge carriers and you have the increased diffusivity due to the solvent. And we showed these results to a couple of experimentalists at Oak Ridge, and they went ahead and measured the conductivity for 4 of these cases. And we got very good qualitative and in some cases quantitative agreement with the experiment. And more recently, our colleagues at Iowa State, at Ames Lab in Iowa State University, measured the self-diffusion of BMEM in 10 solvents. This is a subset of the 20 that we looked at, 20 or so that we looked at. And the remarkable thing was how, for most of these cases, the simulated diffusivity matched the experimental one almost exactly in 8 out of 10 cases, and even as a function of increasing ionic liquid mass fraction. So we were pretty excited when we got this experimental verification. So I've taken quite a while here, but I hope you will agree that with these conclusions that MGI style screening of soft materials requires automating many of the steps that are currently performed by hand, so that you can put them together and automate them. MoSDeF is a environment for automating these molecular simulations. Everything is scriptable, which is important for screening. It's also important from the point of view of reproducibility. Simulations performed within MoSDeF are completely reproducible. All the steps are scripted. You can distribute them online, and it's in line with all the best practices for reproducibility of computational research that I mentioned earlier in the talk. We're developing MoSDeF with other groups interested in this concept of transparency, reproducibility, usability, and extensibility, something that we call the true simulations. And this is our friends at Notre Dame, at Wayne State, at Michigan, and Minnesota, and their codes. And these are just a couple of, I think, the key papers on this. This one up here is where we introduced this concept in molecular physics, where we introduced this concept of true simulations that are transparent, reproducible, usable by others, and extensible. In this article from AICHE journal, we described MoSDeF, and in the supplementary information, we showed how by using MoSDeF, you could perform simulations of the absorption of water into graphene slip pores in a way that demonstrated how the different Monte Carlo codes that we used gave the same results, and the molecular dynamics codes we used gave the same results. I think this is a great example of how, if you invest in using MoSDeF, you can then switch between simulation engines and switch between simulation types from MD to MC very easily. And then this last one down the bottom here is exciting to me. It's Ed McGinn and his group at Notre Dame have released something called MoSDeF Cassandra, which is a MoSDeF-based Python interface for Cassandra, and that has simplified the use of Cassandra dramatically. So I gave you some examples of material screening enabled by MoSDeF, the nanoscale lubrication case, the diffusivity of ionic liquids and organic solvents. All of the resources that I'm talking about are available on GitHub with version control. The easiest thing is to go to mosdef.org, and then it has links to each of these things, the GitHub resources for MoSDeF. So this is a good place to start, mosdef.org. And I'll just finish by thanking particularly the people at Vanderbilt that have been involved with this. Claire McCabe and I have been working together on this, along with a research faculty member, Chrissy Acavella, for at least a decade now. And then there's graduate students, many of whom have moved on now. Our collaborators at the Institute for Software Integrated Systems at Vanderbilt, is the grants that have supported this and the work that I've talked about today and the resources that we've used in performing some of this work. And so I know I took a lot of time. I had a lot of material, but I hope there's at least a few minutes for questions. I'd be happy to answer them.
Thank you so much, Professor Cummings. It is really a pleasure to have you here with us. We are now open to questions. If you want to ask one, please, you can raise your hand using one of the Zoom tools, and you can also write questions on the chat. I would like to remind our YouTube viewers that they can also ask questions using the YouTube chat. So who wants to be the first?
I can start.
Okay, go ahead.
Thank you for this presentation. I think it was very interesting. I wonder about the lubrication. In this simulation, you impose the force or the displacement.
So the simulation is done with a maintaining a constant normal force, and the movement of the two surfaces is so we do these calculations with lamps, and you can in lamps you can specify that a part of the
okay,
at a specific.
You use the lamp. Okay, I know the.
Yeah. So this, I mean, this is I think a part of the reason for using MoSDeF is that if you want to, different codes have different capabilities, right? And so being able to switch between codes based on the capabilities they have is a very useful thing.
Yeah. How these results depend on the concentration, on the surface concentrations? Because
that's a good question, and I don't have the answer off the top of my head here. This is something that's we've looked at surface concentration as a, and maybe one of the students in the group could answer the question for you. But I know that in some of the recent simulations we've looked at surface concentration, and I don't know if any of our, if Co Quach or Justin Gilmer wants to say something about that.
Sure, this is Justin. We've looked a little bit into the surface concentration, but what we've been using was a concentration where the polymers are, they're essentially supporting each other, because we've noticed if we go a little bit lower in concentration, you get a lot less ordering during shearing. They essentially just sort of fall over on themselves. So this sort of concentration that we've looked at is the one that sort of gives us the best performance in terms of shearing while also being stable.
But it means that for different substance, maybe you have different concentrations, is it?
Exactly, yes. Because we're investigating like a PEG backbone for some of these systems. And we definitely have to do some changes to our concentrations because of the flexibility of those backbones compared to just the pure alkane backbones.
Okay, thank you. Thank you.
Mm-hmm.
Professor Richard has a question. You can go ahead.
Oh, hi, Peter. I've tinkered with MoSDeF, but it's been a couple years, and I didn't get too far. I wanted to test out. Actually, I want to do some really simple things. At the time, I was just trying to implement the trap force field and just run an MD simulation for in alkanes, and so I kept running into trouble. It looked like the way that the Fourier was set up in the inbuild, it would do everything with OPLS, but when it came to trap, it didn't work so well. And so what I've been thinking about is maybe a better way to go about it is to define basically map a number of the OPLS site types so that they have identical force fields in many situations, right? And so you might have 10 different CH2 site types in OPLS AA, but there's only one in the trap force field. So would it be easy, maybe the easiest and best, to just define that force field for that all 10 of those types as the same epsilon and sigma? Is that a better way? Or it looked like you guys were doing it like having a separate whole smarts formalism for every different force field, and then that was, I don't know, it wasn't going anywhere.
I mean, I think the students may want to, or somebody from the MoSDeF group, the broader MoSDeF group may want to answer as well. But the trap force field is an interesting case because it's got a lot of edge cases, whether you do 1,4 and 1,3 type interactions and things like that. Intramolecular versus, when do you ignore the electrostatic interactions within the molecule? And so we've been working with Becky Eggerman, who was a former student of Ilya Seidman. She maintains the trap force field page. And so we have been working with her to get our trap implementation correct. I mean, this is, I don't, somebody else could chime in if they want to. I don't know that there's much advantage in trying to merge OPLS, the XML files for OPLS with the XML files for trap. In other words, have something which is at the intersection of these two and diverges for the edge cases. I think it's, it just seems to be cleaner from our point of view to have a set of XML files for OPLS or atom, a set of XML files for OPLS united atom, and the same thing, XML files for trap or trap A, which depending on your pronunciation, all atom and united atom. So, I mean, I don't know that there's any gain in the in trying to merge those two. Is Justin or Co or maybe somebody from Minnesota want to comment on that? Or because I know.
Yeah. So this is Justin again. Hi, Richard.
Hi, Justin.
I'm not entirely sure. I sort of
just
I have
sorry. Can you open your camera, please?
Oh, yeah, absolutely. Sorry about that.
Thank you.
Hi everyone. So one thing that I sort of echo similar sentiments to Peter in that in terms of like how we're sort of organizing these force fields, it does sort of seem more reasonable in the most cases to have these force fields separate and like it exists in separate situations. We definitely are sort of playing around with the idea of also having, you can, use multiple force fields to parameterize the system. That still runs into similar issues though, where if they don't follow the same mixing rules, things like that, so or combination rules, you're gonna run into issues in terms of compatibility between these. And what we've just sort of found in terms of just extending our studies and doing things like that is it does sort of make life a little bit simpler when you are essentially breaking up these force fields into like smaller parts instead of trying to combine them into larger ones, because you do just run into some weird edge cases a lot of the time, and it becomes more time focused on trying to fix the edge cases. But if you're interested, definitely ping us as well again. I know you have some activity on GitHub as well, and we'd be more than happy to sort of maybe have because Gmsl and a lot of our tools have sort of changed and they've always been evolving, so there might be some things that we can do that maybe make that process easier.
Yeah, I would say that if last time you touched MoSDeF was a couple of years ago, you probably want to touch it again because so much has happened in the last
Yeah.
2.5 years since we started this large collaboration with the 7 other university groups. Things have just gone ahead leaps and bounds. Now, a question was asked by, I don't want to say the name because I'll probably butcher it, but the question was in the chat.
The chat.
Santo, I can say, but first.
Yeah. I don't know if Santo wants to ask the question or the professor can read it.
So let me, so when I say the simulations are reproducible with MoSDeF, what I mean by that is, especially if you are doing a new system, for example, you will use the MoSDeF tools to build it. You may actually have to extend the MoSDeF tools to build your specific system. But if you distribute in a repository or add to the you can add, people can add recipes to MoSDeF. And so you could add your specific recipes, you can add them to MoSDeF, and then they're available for everybody else. What I would urge people to do is take a look at, I mentioned at the end, and maybe I should share my screen again, a couple of papers, and those show you how to do this, how you can use MoSDeF to make things. Okay, if you look at this, paper here, oh, I don't want to do that. If you look at this perspective paper here from AICHE journal, that article, the article itself really only talks about MoSDeF itself, but the supplementary information shows you how to do reproducible simulations on absorption of water into carbon slit nanopores. And if you follow the steps in that supplementary information, you can do every single thing that we talk about in that paper. It will take you through the steps for installing all the software packages, running this, and then repositories which contain the runtime scripts and so on for the simulations. And so you can literally exactly reproduce what's in that supplementary information. The same thing is true of this molecular physics paper. The molecular physics paper, again, has a supplementary information in which it has, again, all the steps needed to install all of the software. And this includes installing the simulation codes themselves. This is the case in both of these papers. And then it goes through 3 or 4 examples of calculations enabled by MoSDeF, using MoSDeF. And again, so it's not just MoSDeF itself that enables you to reproducibly publish a simulation. You also have to publish in a repository some of the simulation scripts and things like that. So I suggest looking at those 2 papers and looking at the supplementary information of both of those papers and just following through the steps, and you'll see that these things make, you can reproduce the reported results yourself. It's so much easier today to do this in many ways because you know, I remember the days of installing lamps myself on my own machine and all the dependencies I had to do myself and using makefiles and all that sort of stuff. You don't have to do that anymore, and it's pretty amazing. And Justin has put some examples, a link there to some other examples, I think, of MoSDeF workflows, right?
Yes, that's correct.
We have another question.
I could ask another one if nobody else wants to go.
You can go ahead, Professor.
So one of the force fields that's being developed pretty rapidly, I think he's gotten out in front of Jeff Potthoff, in fact, is Joachim Gross's transferable anisotropic united atom force field. And so, because it's anisotropic, I could ask another one if nobody wants to go.
You can go ahead, Professor.
So, I don't know what's going on. One of the force fields that's being developed.
Uh-oh.
Is it okay now?
Okay, you can go.
Okay. So the key there is that it's this anisotropic united atom, so that the force fields are not at atom centers. And so I'm wondering, does that create a problem for your whole smarts and Fourier and all of that?
Hang on just a second. I'm trying to get back. Okay, sorry, I'm trying to get back into Zoom. So yeah, so anisotropic united atom. This goes back many decades, really, because it was one of the ideas that particularly at the French Petroleum Institute, that was one of their approaches. The bigger question, I think, is the simulation engines supporting anisotropic united atom. And so what our goal is with GMSO is to be able to support a wide range of different force fields. And this is also work that we're doing. We have a collaboration, an NIH, a small NIH funded collaboration with Open Force Field, because they're also trying to develop much more exotic force fields, things with polarizability, and so on. So we are interested in putting in the GMSO these kind of capabilities. But then the question is, such as united atom, anisotropic united atom is certainly something that we could think about how you develop the XML files to put in Fourier for that. But then you have to have a simulation engine that's going to support it. And our simulation engines, as far as I know right now, would not support those. I don't know. I mean, somebody can tell me if I'm wrong here. I don't think LAMPS does. I don't think GROMACS does. So I mean, there's the flip side is, you can support the force field, but is there a open source simulation code that supports those kinds of interactions? I don't know off the top of my head, to be honest.
Okay, thanks. Yeah, I just thought you define a force center and then the MD just goes forward, but I guess it's more complicated than that.
Yeah, it's been, it's been decades since I thought about anisotropic united atom, because that was sort of a thing that came and went. I didn't know it had been. I didn't know it was coming back.
Yeah, it made a comeback. Yeah, he's got, it's a me force field, and he's developed a lot more of the polar interactions, and so his deviations for chemical engineering properties tend to be smaller and more broadly applicable than what Potthoff can do at the moment.
Yeah, as I said, we'd have to think about it, but this is a good time to be thinking about it, because GMSO is a work in progress, and we're aiming for GMSO to be much more powerful and much more general than PARMED. And we have the blessing of the PalmEd developers in that, for that as well. And so this is the time to be giving us feedback about things people would like to see in Gmsl. So, for example, mean potentials are not directly supported in PalmEd because they're exponential 6. PalmEd only supports Leonard-Jones 12.6 for the van der Waals interaction. So that's part of the reason why we started with Gmsl. I mean, you can do the simulation engines could always, you know, the workaround with PalmEd would be to tabulate the force fields. But we want to be able to support a wide range of force fields analytically.
Thank you.
Do we have another question? Professor Turner, Professor O'Connell?
Yeah, I had a quick question.
You can go ahead.
I'm back. It was a great talk. I was curious about some of the your supercapacitor simulations. You know, one of the frustrating parts about ionic liquids are their high viscosities, and so these kind of co-solvent solutions make a lot of sense. But I was curious, have you screened?
Professor O'Connell?
Yeah, I had a quick question.
We're actually hearing a recording of you, Heath. I'm not sure how that's happening, but you were asking about the co-solvent ionic liquids, yeah?
Yeah. I was asking about the co-solvents. I was curious if you have looked at other properties as well. So like the electrochemical stability windows of some of these co-solvents, or vapor pressures or other things to try to narrow that down.
No, we haven't, but it's a good idea to think about. We have a framework there. We could start to look at some of those things. I know that Ed McGinn has a calculational procedure for evaluating electrochemical window, and maybe Ed might be. I think Ed's gone as far as I can tell, but that would be something else that could be screened over. Yeah, I mean, I think the whole point of using ionic liquids is the large electrochemical window, right? It's 4 volts versus 1 volt for aqueous solutions. Although the aqueous solutions are making a comeback, as you may know, at extremely high concentrations, something that what are called water in salt, 18, 20 molar type aqueous electrolytes have actually much higher electrochemical windows than low concentration, ordinary concentration, 1 molar type aqueous electrolytes. So yeah, aqueous electrolytes are making a comeback at the very concentrated end because of the electrochemical window issue.
Thanks.
But yeah, I mean, it's a good point. And the other point that's always made to us by our collaborators is, yes, understanding what makes a great solvent in the bulk may not correlate at all with what's going to happen under confinement inside the electrode. And they always have counterexamples for us. Well, according to you, this would be a better solvent, but according to our experiments, when you actually put them in a device, it's not the case. But
thank you all. See you next week.